Everyone look up, this isn't part of your notes, this is our thought experiment of the day. It says this. A cat runs, it's a cat picture, Mr. Dewick. Yes, we're doing a little internet meme. A cat runs across the floor from 1 to 2, and then from 2 to 3, without changing or increasing his speed. He only changes his direction of motion at location 2. Can we say for sure that a force was exerted on the cat at location 2? Yes, there had to be a force, or no, since his speed didn't change, there can't be a force. What do you think? Mateo?
Yes.
Convince me.
Because the cat wants to keep moving in a straight line, but then a force makes us change it to
Force, vector or scalar? It's a vector. Remember, direction matters. I did the example where two of us pushed, I think it was Mateo and I, we pushed on somebody from either side and nothing happened because our forces canceled. And then when I joined Mateo, the person started accelerating. Force, vector or scalar? Vector. F equals what? And A is also a vector. Acceleration has magnitude and, what do all vectors have? Magnitude and, I'm looking for it begins with letter D. Sierra. Direction. So you can accelerate if you change your speed or if you change your... Did the cat change the direction? Did the cat accelerate? There must be a force. That's what Newton's first says. Okay? Let's move on. Lesson 3. Types of forces. Go to the very beginning, Mr. Dewick. Another little thought puzzle. Example 1 says this. In the top picture, we have 4 people pulling on a rope, and the rope is attached to a pole. In the bottom picture, we have 4 people pulling and 4 people pulling, for a total of 8 people. The tension in the rope in the bottom case is A greater than, B less than, the same as, C less than the tension in the top case. You know what, Hannah, since there's 3 choices, we get to vote, we get to exercise democracy. As always, Dylan, how high you hold your hand up is how sure you are of the answer. Straight up high, I'm positive. Halfway up, I'm pretty sure. Elbow just off the ground a little bit. I'm only guessing because Mr. Dewick will make fun of me if I don't guess, and Mr. Dewick will make fun of you if you don't guess. This is how we learn in science. We hypothesize, and then we test hypothesis. So who says, Mr. Dewick, with 8 people, the force must be greater, twice as big? A. Mr. Dewick, A. A. Mr. Dewick, A. Twice as big. A. No one. Wow. Who says B? Same as. Ooh. I'm even going to stop there. Emma, why is B right? Yeah, it's really a good example of Newton's third law. Forces come in pairs. So if these people are pulling with 1,000 newtons to the left, and this is a tricky concept, but you're getting good at it, Oliver. How hard is the pole pulling in the top diagram? How hard must it be pulling? 1,000 newtons to the... And this is because when someone who doesn't have a physics background hears this, how can a pole exert a force? Inanimate objects must exert forces, otherwise, Maggie, the universe wouldn't work properly. Otherwise, you would all be sinking into the ground like quicksand. The ground must be exerting a force back up on you. And in the bottom, 1,000 newtons, 1,000 newtons. Well done, folks. You're wrapping your brain around this. I'm proud of you. Explain your answer. What was your answer, Emma? So you can say Newton's third if you know that's Newton's third, or if you said forces come in pairs. You could give me a Newton's first argument. You could say since they're not accelerating, the forces must be balanced in both situations, and forces come in pairs if one's 1,000 newtons, the other's 1,000 newtons. All right. The title of today, David, is Types of Forces. The first one I've already introduced to you a little bit. This is the force of gravity. What was the symbol that I used for the force of gravity? I use a capital F and then a lowercase subscript g, force of gravity. What was the equation? Well, Mateo, what did you say? F equals what? M, except we put a g there because we know the acceleration that we want for gravity. What's the acceleration due to gravity on the Earth? 9.8. We ditched the negative in this unit because you'll see why. Later on, we'll be getting to multiple masses where some are moving up and some are moving down and some are moving left and some are moving right. Which way is positive? Whichever way makes the math nicer is what we're going to decide on. But this force of gravity would also work on the moon. On the moon, the force of gravity is also mg. Does your m change on the moon? No. What changes? G. Direction. Make that a little better, G. Direction. Obvious. Which way does gravity act? I heard someone say it. Down. And I would totally accept that. If you really want to put a fancy schmancy, toward the center of the planet. That covers Australia, because their down is our up. Technically. Okay. Toward the center of the planet. What was another word for the force of gravity? And I'm going to be fussy. I'm going to start to use this. What was another word for the force of gravity? No, now. Weight. No, now. Weight. Mass is measured in kilograms, Christy. Weight is measured in newtons. It's kilograms times 9.8. And this allows me to nicely define 1 Newton. Which depends. So, Shelby the ballet dancer has a mass of 45 kilograms. Behind you, actually, back there, thank you. Dylan? And then if we send it up, it'll end up over here somewhere. What's Shelby's weight in newtons at the Earth's surface? Now, Brian, can you read me A completely, please? On a test, I'm not going to give you that hint anymore. I'm just going to say, what's the weight? And if you say 45 kilograms, do you think if it was multiple choice, would I have one of the answers to pick from? 45 kilograms? Yes. In fact, would I make that answer A just to see who's paying attention? Probably, because that's how I roll. So I'm not going to give you that hint on a test anymore. Can I have my mass back, please? Do you feel it? See, about that. Okay. So it wants us to find the weight. Weight is a synonym for the force of gravity. So it's going to be 45. Cole, what? Times 9.8, which is what? I can do that in my head. It's going to be 45 times 10, which is 450 minus 9. Is it 441? Double check me. Yes? 441 what? Units. It's a force. Newtons. I probably won't ask you for a direction for weight. It's assumed it's towards the center of the planet and down, whatever. Given that 1 kilogram of mass corresponds to 2.2 pounds at the Earth's surface, what's Shelby's weight in pounds on Earth? We need to do a unit conversion. We're going to write down what they gave me, 45 kilograms times. I want kilograms to cancel. Where is it going to go in my next fraction? On the bottom. And I think the abbreviation for pound is that the pound sign, yeah? Yeah? Or you can use LBs, which I've never understood how LB comes up with pounds. What's the conversion factor? 2.2. If you're looking, if you ever have to convert kilograms to pounds, which you have to sometimes do in the supermarket or whatever, if you want to get the weight in pounds, double it. What's 45 times 2? 90. Remember that. 45 times 2, 90. Remember that. And then knock a decimal off. 90 divided by 10, 9. Add 9 to it. That's how you go times 2.2. You double it, and you double it by 0.2. Anyways, 99? Yes? Yeah? So LB you can use as your abbreviation, or pounds you can use as your abbreviation. Or you can write the word pounds. And here's what that means, by the way. On a standard bathroom scale, pounds is the unit of force. Pounds is the imperial equivalent of newtons. Kilograms is a unit of mass. And so we're sloppy in English when we say, I weigh this many pounds or this many kilograms. No, you have a mass of this many kilograms. You have a weight of this many pounds. What's the unit of mass in the imperial system? Slugs. Really? Yeah. And no one uses or knows that, which is one more reason why, for Pete's sakes, US, would you please go metric? What would Shelby's mass be on the surface of Jupiter? I know Jupiter's a gas giant, but suppose it had a surface. What would her mass be on the surface of Jupiter? Mateo, loud and proud.
45.
Your mass doesn't change anywhere in the universe. Your mass doesn't change. That's a reflection of how many atoms there are inside of you. That doesn't change. That's your inertia. That's your resistance to force. That's why I'm using mass and inertia interchangeably. That changes when you go near the speed of light, but for now, we'll just pretend they're the same. What would her weight be? Now that's going to change. Weight is location dependent. Mass is not. So her weight is going to be 45 times 25. I can do that in my head as well. I think. 1250? No, that's wrong. 1150? 1125. Wow. Maybe I can't do that in my head. So you ready? Here's the question. Suppose you were near a black hole. Would your mass change? No. Would your weight change? Yes, because a black hole has a very strong gravitational field. By the way, all a black hole is that G approaches infinity. So instead of 9.8 or 25, it's so big that the force required to leave is beyond our ability. It says pause here and complete section A of the homework. We're actually going to finish this lesson, and then your homework is going to be a couple of questions. Let's keep going. So we're not going to pause yet. Put a star next to the title normal force. This is important. And this is going to be a tricky one for you to wrap your brain around. Example 1 says, suppose a 1200 Newton truck is sitting at rest on the ground. Draw a free body diagram of the forces acting on it. Let's represent the truck with a mass. What are the forces acting on it? Get the obvious one. Gravity, which way? mg. Oh, and I know what that is. What's the mass of the truck? Is the mass of this truck 12,000? Brian, how do you know the mass can't be 12,000? I've told you, memorize units. What they've given you is the weight. If I wanted the mass, I would divide by 9.8. That would give me the mass, but I know this is 12,000 newtons. So I could even put a number on there this time. Hannah, is this truck sinking into the ground like quicksand? Is it flying through like Superman? So the forces must be, I'm looking for where it begins the letter B. So there has to be a force up. How big is that force exactly in newtons? What is that? Well, it's the ground. We're going to give that force a special name today. We're going to start to call it in a little second the normal force. Suppose we add a 2,500 Newton piano to the back of the truck. Draw a free body diagram of the new forces. Okay. So now I have 12,000 newtons down, and I have 2,500 newtons down. Christy, is the truck and the piano sinking into the ground like quicksand? Is it flying into like Superman? You just have to use our imagination. Just sitting there. So the forces must be, I'm looking for where the letter B. What's our total force downwards, folks? And what must be our total force upwards then? What is our total force downwards? Can you do the math in your head? 14,500. What must the total force upwards be? So if I gave you this question on a test, Emma, and I said draw the free body diagram, I would take marks off if you did that, because you've just canceled out gravity on the truck, but you haven't canceled out the piano. I would be looking for your upwards arrow to be about the same length of both of those downwards arrows combined. So I would be looking for something like that. Is that okay, Tim? This force of the ground, or any surface, a table, a chair, that pushes up to prevent an object sinking into it, has a special name. We call it the normal force. And the symbol that we're going to use is F with a subscripted N for normal. We'll pause. So everybody right now, take your hand, your non-writing hand, make it flat, push down on your desk. Is your hand sinking into the ground like quicksand? Keep pushing. Brian, keep pushing. Is it flying into you like Superman? So this is a equilibrium situation. The forces are about, push harder. The normal force just got bigger. Push harder. The normal force just got bigger. Ease up. The normal force just got smaller. The normal force is only going to be as big as it needs to be, which means it's a reactive force. Really, it's a result of Newton's third law, which is, Emma? Forces come in pairs. I will never give you an equation to calculate the normal force, but you'll be able to figure it out. How? Because the object is not sinking into the ground like quicksand and not flying into you like Superman. You'll figure out how hard the ground or the table or the surface, how big the normal force is pushing up by figuring out, well, how much is pushing down, and they cancel out. So you'll never get an equation from me on your formula sheet. Here's how you calculate the normal force. You'll figure it out from the free body diagram. It's only as big as it needs to be. It's the force that prevents us from falling, sinking into the ground. So, how big is the normal force in each of the following situations? Exactly. What are the forces acting on this object? Get the obvious one. So we have mg down. Is this object sinking into the ground like quicksand? Is it flying to like Superman? So the normal force must be the same size as mg. How big is that exactly in this case? How would I calculate it? Maggie, what do you type it into your calculator? You're right.
5 times 9.
Yes. 5 times 9.8. 49? Double check me. Yes? Okay. Suppose we have that same object sitting there, but someone's pushing down with another 30 newtons. What are the forces acting on this? Get the obvious one. Get the obvious one. So we have gravity down, and then we have an extra 30 newtons. Somebody off of the screen is pushing down on it. How big does the normal force have to be? It's got to be bigger than gravity. How big is the normal force here exactly? It's going to be 49 plus 30. Where'd the 49 come from?
5 times 9.
Okay, it's going to be mg plus 30. That's how big the normal force is. Which is how big? In your head, please. 79 newtons. Yeah. C. Now, instead of pushing down on this block, someone off the page is lifting up a little bit. What are the forces acting on this? Get the obvious one. So we have 49 newtons down. Why would I take marks off if you drew the normal force the same size as mg? Why doesn't it have to be the same size as mg? How big is the normal force have to be exactly? Can you do the math in your head? Brian, it's got to be 37 newtons. Why? Are we sinking to the ground like quicksand? Are we flying into like Superman? So the forces must be, I'm looking for where the letter B. What's my total force down, grand total? So what must my total force up be, grand total? How much do I have on the page right now? 12 newtons? What else must, this is why Newton's first law is so useful. What else must be there? The normal force must be 37 newtons. And now I need to temporarily blow your mind. I need to ask you what a scale measures. So a scale does not measure mass, does not measure weight, and I'll snap and freak out anytime someone says that that's the case. It can't. What does it measure? It measures normal force. Have I convinced you of that okay? So, when I ask you to find what a scale reads, what I'm really asking you to find is, Cole? What you think of as your weight is actually how hard the chair is pushing up against your body right now and how hard the floor is pushing up on your feet right now. Combine them together, that's what you feel as your weight. A good amusement park ride messes around with the normal force. We cannot change mg, we're not God. What we can do is muck around with the normal force. Put your pencil down. This allows me to do the famous elevator question. I like example 7, example 1, I like example 1, I like example 1, I like example 1, example 1. You're going to see several elevator questions on your tests. What do I mean by an elevator question? A person stands on a scale in an elevator. What does the scale read if the elevator is A, accelerating upwards, B, accelerating upwards, C, accelerating downwards, D, accelerating downwards, and a few other options. Okay. You know what this is a job for? A free body diagram. Do not try and do these without a free body diagram. With a free body diagram, they fall apart. If you try and do these in your head, you're going to make sloppy mistakes. So, I'm going to do my free body diagram for question A right there. There's the person. What are the forces acting on this person? Get the obvious one. Which way? Which way? Yeah. So draw an arrow down, label it mg. And now, Oliver, in part A, which way is the person accelerating according to part A? I'm going to ask you the same question. I'm just going to phrase it differently. I want the same answer. Which way is my bigger arrow going to be pointing? Which way is the winning force going to be pointing? Which force is that? Well, it's the scale, technically. But what does a scale measure? Not mass. Not what? By the way, Oliver, what's this question asking me to find? What does the... It's not asking you to find what the scale reads. What's it really asking you to find? Normal force. Whenever I talk about a scale for the rest of this year, if you're standing on a bathroom scale, I'm talking about the normal force. So Oliver, see my free body diagram? Who's winning? Who's losing? Fn minus winner minus loser. What does winner minus loser always equal? F net equals MA. Oliver, what did you say that we're trying to find? What the scale? What are we really trying to find?
Fn.
How would I get the Fn by itself? How will I move this minus mg over to the other side? Yep. Don't try and memorize these different equations. Memorize that I can figure it out from a free body diagram. So you're telling me, Oliver, that the normal force is going to be ma plus mg? Or mg plus ma? Let's see. Oliver, what's m? Nope. They told you. Go read earlier. M is mass. Measured in? No. Brian, what are the units for mass? Kilograms. What's M?
70.
Yeah, oh, I'm glad you went, because that is meant to be Captain Obvious from now on for you, yes? 72. What's A?
3.5.
Yes, you see, now it's plug and chug time. This is why I said memorize units. 3.2 plus, what's M? What's G? And we're not going to put a negative in here, just 9.8. We've taken care, by the way, we put the negative in by putting a minus sign in front of that at the beginning. That's where we took care of our direction. So 9.8, which is what? Can I do this in my head? It's going to be 72 times 13. So it's going to be 720 plus 210. 720, 210, 930 plus 26. 956? No, am I wrong? 936. Guy, do it. Is that right? 936? Units, Oliver, it's a force. Yes. Now, most scales don't read newtons. Most scales read kilograms. How do I change newtons back into kilograms? Divide by what? Divide by 9.8. On your calculator, how heavy would this person feel right now? What'd you get?
95 pounds.
Not pounds.
Oh.
Units for mass.
Okay.
Kilograms. What was their actual mass? No. What's their actual mass in kilograms? Don't let me down here. 72? What's their apparent mass? 90. They feel like they're 95 kilograms. Okay? This is why, for example, if you do a free body diagram on a roller coaster at the bottom of a hill, trust me, you'll feel heavier at the bottom. Has your mass changed? No! What has changed? The normal force. On the elevator, if you do the free body diagram for that, when it's shooting you up, you feel like you're getting pushed down, not because you're getting pushed down, but because the normal force is bigger than you're used to. What if we were accelerating upwards at 2.5 meters per second? This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one, Rihanna. Yep. Which way is this person accelerating? Which way must there be a bigger force pointing? Did you say upwards? Yeah?
Yeah.
Which force is that? It's the scale, but what does a scale really measure? So we get this. I always exaggerate it. What am I going to get for an equation? Who's winning? Who's losing? What does winner minus loser always equal? MA. We get the same situation as Oliver. Don't try and memorize this, and it won't always be the same. I can come up with a million ways to vary this. We can figure it out, though, from the free body diagram. How would I get this normal force by itself, Rihanna? I wrote mg plus ma, but ma plus mg. Now, right now, all of you, look up, don't write this down. All of you are feeling this right now because you're not accelerating. Forces are balanced. If you're accelerating upwards, can you see you must feel heavier because it's gravity plus something? That's why you feel heavier when you're accelerating upwards. What you think of as your weight is actually the normal force pushing up through against you. So it's going to be 72 times 9.8 plus 72 times 2.5, which is what? You get 885.6. Is that right? 886. If you said that, I'll go 885.6. If you feel heavier when you're accelerating up, what should you feel if you're accelerating down? Sierra? Let's prove it. Sierra, which way are we accelerating in part C? And it wants us to find the normal force. You know what this is a job for, Sierra? Here's the person right here. What are the forces acting on this person? Get the obvious one. Yep. What else? There has to be a force up because if there wasn't, the acceleration would say 9.8. Are we accelerating down at 9.8? No. So are we in free fall? No. So I know there has to be a force up. Which way are we accelerating? Which way is the winning force going to be pointing? So the force up is going to be smaller. What force is that? I'm still standing on a scale. Yep. Who's winning? mg, winner, minus. Who's the loser? What does winner minus loser always equal? What am I trying to find according to this question? What the scale reads. What am I really trying to find according to this question? How would I get the normal force by itself? What's right in front of the Fn that I don't like? A subtraction sign. I think I called this the other day the swappy dance. We're going to do this very often. The normal force has a minus in it. I'm going to plus it to this side. Everybody draw the little loop pointing there. That's my way of saying, David, I'm going to plus it to that side. But at the same time, I'm going to minus the MA to that side. Why minus the MA? Because the MA is positive. And so what I end up getting here, Sierra, is the MG drops down like a domino. There's a minus MA. And Sierra, do you mind? I'm going to put the equals Fn on the left-hand side because that's where I like to see it. Look up, look up, look up, look up, look up. Normally, your normal is that. But when you're accelerating down, are we subtracting from our total? That's why you feel lighter. You must get a smaller answer if you subtract. That's why on the way down you feel lighter. What was M, Sierra? G, 9.8. Oh, when you're subtracting, the order matters, by the way, so don't subtract in the wrong order. Minus 72 times 5.2. What's the normal force? 72 times 9.8. By the way, you may find, if you're clever, that you could just backspace on your calculator and save yourself some typing. Change the plus to a minus, and yeah. 331.2. Now, that's if the scale read in newtons. Do scales typically read in newtons? So that's why it also asks, what would this read in kilograms? So I'm going to write the word or. How would I convert that to kilograms? Because, yeah. Divide by 9.8. 33.8 kilograms. Kilograms and force aren't the same thing, so I'll call this maybe part A and this part B. I'll put a little B there. Is that okay? I'm going to skip D. You can try it yourself if you want. I'm going to do E. I'm going to do E. What does E want me to find? Normal force. You know what it's a job for? I'll do my free body diagram right here. Mateo, what are the forces acting on this guy? Get the obvious one.
Gravity.
Which way?
Downwards.
Okay. What else? Are we standing on a scale?
Yes.
So ground is pushing up. What does the scale really measure? Which way?
Upwards.
Bigger, smaller, the same size as mg. Which way are we moving?
Downwards.
Okay. Who's winning? Gravity? Who's losing? Fn? What does that equal? Ma? Why are you shaking your head, Mateo?
We're moving at a constant velocity.
Oh. So if this is a constant velocity, what does A equal? So you're telling me this equals 0? Yes, absolutely. So I can still go winner minus loser equals MA, but what's A?
0.
So what's M times 0?
0.
So I really have this. I have M mg minus fn equals 0. How to get the fn by itself? Plus it over because it's got a minus in front of it. Will that change any? You know what? I get that. What's all of your normal force right now? mg. What's the normal force if you're moving at a constant speed? mg. This goes back to Isaac Newton. This is why he said, boy, there is no way, there is no experiment you can do in the universe to tell whether you're at rest or moving at a constant speed. We can detect acceleration, but we can't detect velocity. We can't. So, Fn is going to be mass 72 times 9.8. It's going to be 720 take away 14, which is going to be 706 take away... I forgot to carry a 1. 705.6. I should have had that. And if you divide that by 9.8, they feel their normal. They feel their normal mass. They can't tell they're moving at all. Last one. Can you do F in your head? Supposing the elevator snaps, the cable snaps, and I'm in free fall, and I stand on the scale, what will the scale read? Zero. Let's prove it. Now, if you figured that out on your own without doing a big proof, I'd give you full marks for not showing the work. But let's prove it. What are the forces acting on this person? Get the obvious one. Which way? What else? I'm not sure. I'll put a little tiny normal force just in case. I definitely know gravity's winning because which way are we accelerating? Who's winning? So I get this. mg, winner, minus normal force, loser, equals ma. How would I get the normal force by itself? Time for the swappy dance. And I get this. mg minus ma. Brian, do you mind? I'm going to write the normal force by itself over on the left side. Normal force equals, what was m, Brian? 72? G, 9.8 minus 72. Brian, what was our acceleration? No, read. Yeah. What's 72 times 9.8? Take away 72 times 9.8. Don't calculator. It's anything take away itself. You've just proved that when I jumped out of an airplane, I mentioned I jumped out of an airplane, I wasn't weightless. Gravity was still there. I was normal forceless. And that's what you feel when you're in the air. It's not that you don't feel gravity. You don't feel the ground pushing back up on you. That's what weightlessness is. Okay. What's your homework? Section A, all of it. And Section B, lots of elevator questions. So every question. Brian, what was that?